Hi everyone, welcome to Unit 14 of online course on probability distributions. In the last unit, we have discussed Poisson distribution and its different generating functions. Probability generating function, moment generating function, cumulative generating function. And after getting moment generating function, we have discussed how we can find arbitrary moments of the distribution. And after getting the cumulative generating function, we derive the cumulants of the Poisson distribution, and we obtain that all cumulants of the Poisson distribution are equal and equal to its parameter value. Now, we move on to finding mode of the distribution. As we all know, Poisson distribution is a distribution of the discrete random variable, and in order to find the mode of the discrete random variable, we are finding the value of the random variable by which the probability mass function is maximum. So, in order to get the mode of the distribution, we are finding the value of the random variable x, by which the f of x value has the maximum value. And how we are finding that value? That is, if x is the mode of the Poisson distribution with the parameter lambda, then mode x is obtained by lambda minus 1 less than or equal to x less than or equal to lambda. And to derive the mode of the distribution, we make use of the concept that if x is the mode, the f of x is greater or equal to f of x minus 1 and f of x is greater or equal to f of x plus 1. So, you are given x as the Poisson random variable and the f of x value is equal to e power minus lambda power x divided by x factorial. And to get the mode of the distribution, suppose we assume x as the mode. If f of x is x as the mode, then f of x is obtained by identifying these two inequalities, f of x greater or equal to f of x plus 1 and f of x greater or equal to f of x minus 1. You find these two inequalities and simplify from these two inequalities. Combining these two inequalities, we have the value of the mode of the distribution. And when we are considering the first case, f of x greater or equal to f of x plus 1, you substitute the values of f of x and f of x plus 1, and that is e power minus lambda power x divided by x factorial, that is f of x, greater or equal to f of x plus 1, that is e power minus lambda power x plus 1 divided by x plus 1 factorial. And from this left hand side expression and right hand side expression just note, and common factors cancelling, e power minus lambda will be cancelled, and lambda power x and lambda power x plus 1, and remaining only one lambda here, and this lambda power x will be cancelled, and x factorial and x plus 1 factorial and common factor. When we are cancelling the common factors, this become 1 and this is x plus 1. So, finally, we have the case 1 greater or equal to lambda divided by x plus 1, and from that we have x greater or equal to lambda minus 1. So, we have the inequality, this is the first inequality we have, x greater or equal to lambda minus 1. So, that is, if x is the mode of the distribution, we derived that x is always greater or equal to lambda minus 1. And again you consider the second inequality, that is f of x greater or equal to f of x minus 1, when we are considering f of x greater than or equal to f of x minus 1, that is equal to, again you substitute the values f of x and f of x minus 1, then that is e power minus lambda, lambda power x divided by x factorial greater than or equal to e power minus lambda, lambda power x plus x minus 1 divided by x minus 1 factorial. As in the previous case, here also you cancel the common factors from the left hand side and right hand side, then the remaining factor will be, here it is e power minus lambda will be cancelled and lambda power x and lambda power x minus 1. So, there remain 1 lambda and x factorial and x minus 1 factorial, there remain 1 x. So, this side become 1 and this side become lambda by x, and simplifying, this is x less than or equal to lambda. So, this is our second inequality. So, just note, first inequality is lambda minus 1 less than or equal to x. This is our first inequality we obtained, and this is our second inequality. So, combining these two inequalities, we have lambda minus 1 less than or equal to x less than or equal to lambda. So, what we derived here is, if x is the mode of the Poisson distribution with parameter lambda, that mode x is obtained by identifying the inequality lambda minus 1 less than or equal to x less than or equal to lambda. Remember, x is a discrete random variable, and random variable having the values, for Poisson random variable having values 0, 1, 2, etc. So, that means the value of the x in between lambda minus 1 lambda, all values are not admissible, only the integral values are admissible. So, because x is a Poisson random variable, and so x have only values 0, 1, 2, 3, etc. So, if lambda is an integer, suppose lambda is an integer, say I, then this inequality reduces to I minus 1 less than or equal to x less than or equal to I. Suppose lambda is an integer, say 4, this become 3 minus 1 less than or equal to x less than or equal to 4. And what are the possible values for x? Since x is a Poisson random variable that have only integral values 0, 1, 2, 3, etc. So, that means all the values are, it may be I minus 1 or I. So, x have the value I minus 1 or I if lambda is an integer. So, in that situation, the Poisson distribution has two modes, that is mod at lambda that is equal to an integer I, or lambda is equal to I minus 1. So, that means probability mass function is maximum at two values I and I minus 1. That is, Poisson distribution is a bimodal distribution. There are two modes for the distribution. Instead of lambda as an integer, suppose lambda is a fact, the quantity is something like this I plus f, that is I the integral part and a fraction part, say 2 plus 0.5, suppose 2.5. So, if it is, what is the mod? The mod is, in that case, this is I plus f minus 1 less than or equal to x less than or equal to I plus f, where I is the integral part of the lambda and f is the fraction part. So, in between I plus f minus 1 and I plus f, what are the possible values of x? Here also you just note that x is an Poisson random variable, and so having only integral values. So, in between these two quantities, there exists only one integral value, that is I, the integral part of the lambda. So, if lambda is equal to I plus f, if lambda is equal to an integer plus a fraction part, then x value is equal to I. That is, if parameter of the Poisson distribution is not an integer, then there exists only one mod, that is, it is a unimodal distribution. So, once again I repeat, for a Poisson distribution, we can find the mode of the distribution by finding this inequality lambda minus 1 less than or equal to x less than or equal to lambda, and identify the character of lambda. If lambda is an integer, then there exist two modes, I minus 1 and I, where I is the value of the lambda. If lambda is not an integer, then the integral part of the lambda is the mode. So, there exists only one mode. So, that is the result we have. That is, this is a, if lambda is an integer, there are two modes for the Poisson distribution, one at lambda and another at lambda minus 1 bimodal. And if lambda is not an integer, there exists only one mode, that is the integral part of the lambda. Okay. So, this is the situation regarding the mode. And to understand the concept of, to understand the way in which we are finding the mode, we just consider one example. Suppose x is a Poisson random variable with the parameter 3. So, as discussed regarding the mode, the derivation of mode, here lambda is equal to 3. Suppose the first example, if you consider, here lambda is equal to 3. So, lambda minus 1, that is 2 less than or equal to x less than or equal to lambda, that is our 3. So, the if x is the mode of the distribution, then x is always like this, 2 less than or equal to x less than or equal to 3. So, what are the possible values of x in between 2 and 3, including 2 and 3, 2 less than or equal to x less than or equal to 3. How many integral values are there? There are two integral values. Which are they? 2 and 3. So, x have the value 2 and 3. So, mode of the distribution lies at 2 and 3. There are two modes for the Poisson distribution with the parameter 3. Similarly, second example, when we are discussing the second example, here lambda is given as 1.7. That is not an integral. And so, lambda minus 1, that is our 0.7 less than or equal to x less than or equal to lambda, that is our 1.7. So, if x is the mode, by the inequality that we derived, we can write that x lies between 0.7 to 1.7. And in between 0.7 and 1.7, what are the possible values for x? The possible value is only one value, that is x is equal to 1, because in between 0.7 and 1.7 there is only one integral value, that is 1. So, for that case, the distribution is unimodal, only one mode, that is probability mass function is maximum at corresponding to the value x is equal to 1. So, these are the examples with regard to mode of the distribution. And now, we move on to another character of the Poisson distribution, and that is very important property of the Poisson distribution, that is regarding the conditional distribution. So, you are given that two independent Poisson random variables given to you, that is x and y are independent Poisson random variables. Then what can you say about conditional distribution of x given the sum of the random variables? And a very important result is that if x and y are two independent Poisson random variables, then the conditional distribution of x given x plus y follows binomial. So, that is, suppose you are finding probability of x given x plus y. So, that means probability of x is equal to some k given x plus y is equal to n. We have to prove this probability is nothing but binomial probability mass function. And how we establish this result? See, we started from probability of x is equal to k given x plus y is equal to n. Remember, you are given that x is a Poisson random variable, let it be a random variable with the parameter lambda and say lambda 1, sorry. Suppose it is lambda 1 and y is another Poisson with the parameter lambda 2, suppose. Then we are finding what is the probability of x is equal to k, and these are independent also. Remember, these are independent. And our aim is to find the conditional probability of x given x plus y. And so you consider this probability. Consider this probability x is equal to k given x plus y is equal to n. And using the definition of the conditional probability, this is same as probability of x is equal to k intersection y is equal to n minus k divided by x plus y. So, because this is actually probability of x is equal to k, x plus y is equal to n divided by probability of x plus y is equal to n. And that is reduces to already x have the value k. So, this x plus y is equal to n reduces to this is k, because already x is taken as the value k. So, this is y is equal to n minus k divided by x plus y is equal to n, and that is equal to probability of x is equal to k into probability of y is equal to n minus k divided by probability of x plus y is equal to n. Why we are writing like this? Because you are given that x and y are independent. So, if x and y are independent, probability of x is equal to k intersection y is equal to n minus k can be written as the product of the probabilities. Probability of x is equal to k into probability of y is equal to n minus k. Just to substitute the probability values. How we can substitute the probability values? We know x is a Poisson random variable with the parameter lambda 1, that is our assumption. So, what is probability of x is equal to k? Probability of x is equal to k is e power minus lambda 1 into lambda 1 power k divided by k factorial. That is a Poisson probability mass function. Similarly, you are given that y is equal to, y follows Poisson with lambda 2. So, if it is the probability of y is equal to some y is e power minus lambda 2 into lambda 2 power y divided by y factorial. So, these are the given probability mass functions if we are assuming x is a Poisson with lambda 1 and y is a Poisson with lambda 2. Substitute, and again one more thing we can write, since x and y are independent, x plus y follows Poisson. By additive property of Poisson random variables, we can write this lambda 1 plus lambda 2 as the parameter. Make use of all these arguments and substitute here. This is equal to probability of x is equal to k, that is e power minus lambda 1 power k divided by k factorial into probability of y is equal to n minus k. Probability of y is equal to n minus k is obtained from here as e power minus lambda 2 power, this is n minus k. So, n minus k power n minus k divided by n minus k factorial. That is the numerator quantity. That divided by probability of x plus y is equal to n. That is, since x plus y is a Poisson with lambda 1 plus lambda 2, you can write this value as e power minus lambda 1 plus lambda 2 into lambda 1 plus lambda 2 power n divided by n factorial. So, starting from the conditional probability x is equal to k given x plus y is equal to n, we derived up to this. From this, it just not in the numerator there is e power minus 1 and e power minus 2 lambda e power minus lambda 1 and e power minus lambda 2, and denominator e power minus lambda 1 plus lambda 2. So, cancelling the common factors. So, this is answering, we have remaining factors we have, and what is the final quantity we have. Finally, we have this not lambda 1 power k divided by k factorial. So, lambda 1 power k divided by k factorial, okay, and then lambda 2 power n minus k divided by n minus k factorial, lambda 2 power n minus k divided by n minus k factorial. That is about the numerator, whole divided by, see, in the denominator we have lambda 1 plus lambda 2 power n divided by n factorial. So, lambda 1 plus lambda 2 power n divided by n factorial, and that is, you combine the factorials. So, this n factorial, the numerator, k factorial, n minus k factorial, okay. Then the remaining factors are lambda 1 power k, lambda 2 power n minus k, that divided by lambda 1 plus lambda 2 power n. And instead of writing lambda 1 plus lambda 2 power n, let me write this as lambda 1 plus lambda 2 power k into lambda 1 plus lambda 2 power n minus k. That is, you split the denominator factor lambda 1 plus lambda 2 power n like this. The advantage is, this is nothing but, see, this factor is our NCK. So, NCK. Then we have and lambda 1 divided by lambda 1 plus lambda 2 combined, and power is here k. So, that is, this factor and this factor are combined into next factor lambda 2 divided by lambda 1 plus lambda 2 power n minus k. So, let me write this as NCK p power k q power n minus k, where p is equal to lambda 1 divided by lambda 1 plus lambda 2, and q is 1 minus p, that is lambda 2 divided by lambda 1 plus lambda 2, and what this is nothing but our binomial probability mass function. So, here we establish that if x and y are two independent Poisson random variables, then the conditional distribution of x given x plus y is a binomial distribution. Once again, if x and y are two independent Poisson random variables with respective parameters lambda 1 and lambda 2, then the conditional distribution of x given x plus y is a binomial distribution. And corresponding to this result, we can have the converse part of this also. and the converse part can be described like this. If x is a Poisson random variable and the conditional distribution of y given x is binomial, see, if x follows Poisson with parameter lambda and conditional distribution of y given x is binomial with the parameters x and p, then y is a Poisson random variable with lambda p as parameter. This is a result something of that is with regard to earlier result we have, if x is a Poisson, y is a Poisson, then x given x plus y is a binomial. Here it is, if x is a Poisson and the conditional distribution of y given x is binomial, then y is a Poisson random variable with the parameter lambda p. So, that result can be established using the usual procedure, that is, you are given that f x follows p lambda, you are given x follows p lambda, and the conditional distribution of y given x is given as binomial with the parameter n and p. These are the two factors you are given. And when we are considering the first one, x given p lambda, our probability mass function is this one, f of x is equal to e power minus lambda, lambda power x divided by x factorial. And what about the conditional distribution? You are given that conditional distribution of y given x is a binomial distribution, and parameters are also mentioned there, x and p as the parameter. So, probability of y is equal to k, x is equal to x is equal to x c k p power k q power x minus k, where k is equal to 0, 1, 2 etc. up to x. See, 0, 1, 2 etc. up to x for the value k. These are the two factors given to you, and from this our aim is to prove y is a, that is this random variable, y is a Poisson random variable with the parameter product of the parameters lambda and p. Lambda is the parameter of the Poisson random variable and p is the probability of getting success when we are considering the conditional distribution of y given x. And so, the y is a Poisson random variable with the parameter lambda p, that is the result we have to prove. And to get that result, you consider this. See, probability of x is equal to x, y is equal to k, you are given, you can write this as this way, probability of x is equal to x, y is equal to k is the joint probability mass function of x and y, and that can be written in this way also, that is probability of the univariate random variable x into the conditional distribution. See, you know this probability of a given b is equal to probability of a intersection b divided by probability of b. So, probability of a intersection b can be represented as probability of b into probability of a given b. That way we can represent the probability of a intersection b. Apply this concept here, probability of a intersection b is equal to probability of b into probability of a given b. So, that is our value, and substitute the cases. Substitute probability of x is equal to k, x is what? It is a Poisson random variable, and so e power minus lambda, lambda power x divided by x factorial is the probability value. And what is the given? The conditional distribution of y is given, that is binomial with the parameter x and p. So, x c k, p power k, q power x minus k. Hence, how we can find the from the this is joint probability mass function, from probability of x is equal to x, y is equal to k. Suppose we are finding probability of y is equal to k, the procedure is you find the sum of joint probability mass function over all the values of the first variable. First variable here is x. So, this is the way we are finding the marginal probability when the joint probability function is given to you. So, on the basis of this result, we can find the probability of y is equal to k as sum of this probability joint probability mass function over all x values, and x can have the values from k to infinity, because this is the case when probability of x is equal to x, y is equal to k is given to you, and that is summation of over all x values of this joint probability mass function, and that is starting from k to infinity. And so, this is x is equal to k to infinity, and this is value already we have substituted. So, simplifying that expression, you will get the e power minus lambda is taken outside, sigma x is equal to k to infinity x c k, and combine the factors p power k, lambda power x, q power x minus k divided by x factorial. You can write this expression as e power minus lambda, this is lambda power x is this lambda power x, x factorial, k factorial, x minus k factor, p power x, q power x minus k. That way we are writing. See, this is an additional quantity we introduced to the, that is nothing but 1, and this x factorial is there, and k factorial here x minus, this is actually this is this one, okay, and this x factorial is taken to with this, and this p power k, this one, q power x minus k. And why we are writing like this? Because we can combine the factors. See, e power minus lambda and lambda power x, p power k, q power x minus k. From this, what we are doing, you combine lambda p power k here, and so there is lambda x minus k remaining inside. So, this is lambda power x, this lambda power x is written of the form lambda power k into lambda power x minus k. So, that is this lambda power k and p power k combining, you will get lambda p all power k divided by k factorial into the remaining factor, and this is so e power minus lambda, lambda p power k divided by k factorial is equal into sigma x is equal to k to infinity lambda power x minus k divided by x minus k factorial q power x minus k. And after this, you just find what is the summation of this quantity, that is obtained by this e power minus lambda, lambda p power k divided by k factor, the first factor, and second factor is sigma x is equal to k to infinity lambda power x minus k divided by x minus k factorial q power x minus k, that is equal to the same factor here lambda e power minus lambda, lambda p power k divided by k factorial, and you combine this factor lambda q power x minus k divided by x minus k factorial, x is starting from k to infinity, and this is a non summation for us, because it is the summation of e power lambda quantity, and that is equal to this is e power lambda q. And so, e power minus lambda, lambda p power k divided by k factorial e power lambda q, you combine, you have e power minus lambda, lambda p power k, e power this lambda q can be written as e power lambda into 1 minus p k factorial. Simplifying, this is e power minus lambda p, because it is e power minus lambda, lambda p power k and e power lambda into e power minus lambda p is this one, e power minus lambda and e power lambda will be cancelled. So, the remaining e power minus lambda p and lambda p power k divided by this factorial, and that is our Poisson probability mass function with the parameter lambda p. So, in order to prove the result, Actually, we are considering the definition of the conditional probability and apply the probability mass function values there and simplify the expression, you will get the probability mass function of y. So, if you are given, this is the result we have, if x is a Poisson random variable and the conditional distribution of y given x is binomial with the parameters x and p as x and p as the parameter, then y is a Poisson random variable with the variable parameter lambda p. So, this is we establish using the concept of joint probability mass function you just find using the definition of this probability joint probability mass function is given by the product of conditional distribution and marginal PMF, and from that you find the probability mass function of y is equal to k by taking the summation over all x values, and that summation is simplified, that is some factors taken together and using the usual summation infinite series sum value etc., and that reduces to the form of e power minus lambda p into lambda p power k divided by k factorial. So, when you are given a Poisson random variable and a connection with the binomial random variable, that is regarding conditional distributions, we established these two results. So, with this I think the almost all the properties with regard to Poisson distribution we have discussed in the last module and this module, and now we have to consider some numerical examples with respect to Poisson distribution, binomial distribution and earlier Bernoulli distribution, uniform distribution, and that numerical examples will be discussed in the next module. So, we wind up this session here. Thank you for listening. Thank you once again.